Alright, welcome back. So we are talking about queues and DECTs. We finished queues. Now let's talk about DECTs. And this is going to be probably, given what we know, the easiest data structure or slash ADT you have ever seen in your life. So the DECT ADT. What it does is it kind of works as a queue on both ends. So what it stands for is double-ended queue. Okay? Maybe I should put that in bold instead of quotes. How about that? And so because of that, you have operations to get the front and the back. You can also push to the front or push to the back. And you can also pop to the front and pop to the back. And again, of course, there's empty. So those are your operations. It's really not too bad. I don't know the best way to draw it other than drawing it like a queue. But here's the idea. Let's start out with an empty queue. And let me show you how you might use this. You could, I don't know, push either to the front or the back now. Front, 1. So now we have 1 in our deck. And then we could push front again. 2. Now we have 2, 1. And then we could have push back. Oops. Three, and then we have 2, 1, 3. And this really isn't a whole lot that's new, really. It's just it's a queue with 2 ends that you can go and look at. Okay? So it's like you got some people waiting in line, all patiently. They're pushing back, and then you got some people that are just cutting up to the front, like they want to talk to the manager. Okay, so that's the idea. And then of course you can pop from the front or the back. It could be like pop front. That's the normal thing. Like the first person like gets taken care of as normal. We have 2, 1 left, and then maybe we can pop back. The dude at the end was like, I'm tired of waiting. I'm leaving. So that's essentially the operations that you get, and they should make perfect sense now that we've talked about both queues and stacks. Really, this is mostly a queue again. Okay, so it should be very, very obvious how to implement this with a list because, well, you just use the same operations that you have in a list already. So just use these same list operations. Call it a deck. So the one thing that you don't get with a deck is access to the middle. So it's still a little bit less than a list in that we don't have access to the middle, and I'll talk about that in just a couple more slides. So you've already implemented these things for linked lists. Implemented them for the list ADT, and well, you can just reuse them to implement a deck. You just wrap it around a list, call it a deck. Class deck. It's like, I have all these operations, dot dot dot, front. That's an ampersand. Dot dot dot. I don't know, void. Push back. TX, whatever you want to call it. Dot dot dot. And the one main thing is, deep down, maybe in your private member variables, you're storing a list. Call it capital L or something. Who knows? That's essentially that. And so on this list, you're calling all these operations, and that is your deck. It's a front for a list. That's all. Okay? You're just going and doing all these operations on the underlying list and only giving these to the user to use. You don't get access to the middle. And so, well, these running times, they're just the same as all the list running times, and so we can talk about them quickly. And maybe I should draw the fact that these are just the same as lists. Like this is empty list. This is the list with just 1 in it. This is the list with 2 first and then 1. Then we have 2, 1, 3, and so on and so forth. Okay. Well, if they're the same as the list operations, they're the same, they're the same running time as the list operations, the same space complexity as the list operations. Because all you're doing is calling those things in one line of code, so using constant work to call these list operations. Okay? So it's whatever they are. So front, just go and look at your list, dereference a couple pointers, same for back. So then you got your push front, you got your push back, pop front, and pop back is O of 1 if a doubly linked list, and O of n if it's a singly linked list. Okay? Because otherwise you gotta like iterate through to find the second to last element. That's hard to find. This one we have the next immediately, and so it's easy. This one we have the previous immediately because it was the old back. That's why it makes sense. Hopefully that is not too bad. And then empty is of course O of 1 for the 2 reasons that we talked about for queues. Like, well, either you're keeping track of your size in some member variable somewhere, or you're just looking at the list itself and checking like, hey, is first, does that hold the null pointer? Does that hold 0? Like, it's pointing off into nowhere. That's the idea. So the running times is exactly the same as for lists, and just to make it clear, it's in between lists and stack/queues, but I guess really we should say, I don't know, probably just queues. I guess let's talk about both of them. So stacks you implement with lists. Yep. You get access to, depending on how you implemented it, of course. Let's pretend that pushing to a stack adds to the, I don't know, adds to the end. Or let's make it so that it works for a linked list. So that's singly linked. So let's have it push to the front. Gives you access, push and pop from the front, to the front of the underlying list. Push to it, pop from it, etc. Look at it. That's a stack. Queues, they give you limited access to the start and the end, front and the back, of the underlying list. So, for example, you can push to the back, but you can only then pop from the front. Those are your options. You are forced to do those things. Okay? So, for example, you can't push to the front, etc. Obviously, you can do all these reversed if you wanted to, at the expense of running time, depending on your linked list implementation. And then DECTs now, they give you limited access to, well, they give you full access to the front and the end. But to nowhere else. And when I say that, I'm talking about the textbook version of the ADT. You go off and look at any textbook, it's not going to give you access to the middle of this underlying list. Whereas the C++ DEC just might happen to have an iterator. So that is special. Okay? That's all I want to say there. And so you got your lists where you can access everything. I can obtain a pointer to right here and mess with it. But for all of these, no, I have to pop first. I got to make this the front or the back, the top or the front, whatever you want for your for your underlying data structure. So can't immediately get here. And I mean, the whole reason that we're using these instead of lists is that they make your life easier. If you cannot get to the middle of the list, you don't have to worry about needing to get there. You don't have to implement that process, that function, that method. It keeps your implementation simpler, and it makes your tests easier to write because you don't have to worry about manipulating the middle values. You only get the front and the back. That's all you have access to, at most. All right, so that's the idea. These simplify what you can do with a list, and that simplification makes your life easier as a programmer. Okay, giving you fewer options to solve your problems. And so if these are ever enough for you, one of them, then you have some strong guarantees about what you can and cannot do, and that is useful. Okay, that's the idea. So let's look at C++'s implementation of the DECT ADT, and of course, let us go straight to the docs. Here it is. These are all containers, DECT. And so if you read about this, it's fun. Here's the class itself. You can read up about it. It's very interesting. So one thing that let's see, how do we want to talk about this? Where do I want to say this? It is generally implemented as a dynamic array, okay? So it's actually using a vector deep down. You can use a list. It uses the vector in a very special way to guarantee things, though, because you know that popping from the front of a vector will have to shift things over, okay? And if you scroll down here, its complexity is constant. So it's doing some fancy stuff with its vector that is a little beyond where we are right now. But just know that it's still constant, what it's doing, but it's not shifting the elements anymore once it deletes from the front. That is very special. Okay? And yeah, I think that's all I wanted to say about that. Yeah, DECTs are not guaranteed to store all of its elements in contiguous storage locations. It knows where the front is, it knows where the back is, but it might wrap around a little bit. So don't mess with that. But because it implements it with a vector or something that you have access to individual elements of, it lets you access those things. It lets you go like to the index 0 of your deck, and it doesn't have to be where you thought it doesn't have to hold what you thought it was supposed to hold if you've done some operations on it. So you should stick to the normal things that we know about, and probably use a vector if you ever wanted these. Okay? These single element accesses. So you got your push back, push front, pop back, pop front. That's all the ones there. You can then go to the, let's see, the beginning or the end and get the value. And yeah, check if the size was empty, things like that. So it's implemented all this nice stuff for you, but also some extras if you ever think about needing them. So I want to go to the slides. Well, here's my one example that I came up with for DECTs. It's you go to Disneyland, you get a fast pass. Okay, so you, a good citizen, you push back when you get in the line. Like you got 50 people in the line. Boop, 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 boop. Here's you in green. Boop. With your mouse, ears, hat. And you go to the back because you are nice to people. You want to wait in line. And the people who got fast passes, they get to go right here. They get to push front. How dare they? We don't like them. I'm going to draw them in red. With their hats. And so that is, in essence, how you can model something from real life with a DECT. It's really hard to think of a good example for this. There's a very complicated example that has to do with like scheduling things inside of a CPU, I think, and that is not where we need to be right now. So here is your one example of a DECT, Disneyland's FastPass. So most people push back, but you can also push front sometimes. Okay, that's why you might want to use this. And DECTs have iterators, so you can actually access through the whole thing, and I think I'll show you that. Let's see, you can go from the front to the back or the back to the front. You can go in reverse. So yeah, let me give you an example of that, and we'll go from there. So make dir lecture 14. Here I am, and here we are. So I'm going to include DECT. Here we go. DECT of, I don't know, ints, our favorite thing to put inside of our containers that we practice. Call it D. And, I don't know, we will push 1 to the front, 2 to the back, and then, I don't know, do this all over again to like 3 and 4. So now we have a list that looks like this. We initially had 1 at the front, then 2, then at the front we put a 3, and then at the back we put a 4. So it looks like that, and we can iterate through it. Okay, we can say, well, you can do the cool way, the cool new C++ way, or the old way that always still works, using iterators. You can use begin and end. Alright, so start it off at the beginning, and then just keep on iterating. Okay. For the DECT of ints, and it's an iterator to them, it equals d.begin, and you can go in reverse order by using rbegin and rend. Begin, it is not equal to d.end, it plus plus, or plus plus it, whichever one you like. And let's go and iterate through this. Let's print out our 3, 1, 2, 4. Star it, and then I'll use spaces, I guess. That looks about right to me. So let's make this happen. There it goes. There it goes. 3, 1, 2, 4. Oh my. It all worked out, and we could pop from the front and pop from the back. It's essentially a list at this point. You can go in reverse order. I do want to remind you of those cool new things from C++ 11 and later. We're using 17 now. And that's a long type. I want to type it. That's one thing you can do. Let's make 2 endos here. It's one thing you can do to use this to do the same thing. Auto will figure out, because we called d.begin and we're setting it equal to that. It knows this return type of d.begin. They can figure that out. C++ 17 or 11 and later does the same thing. Also, we can use the range-based for loop. We can do for auto x in d. For every element in d. Oh no. Call it x, and it picks it out, and really it's supposed to be an int, right? It gets out every int x. Call in inside of d, calls it x, prints it out. And then if you were lazy about figuring out what type it was, but it's still one extra character in this case, you can say auto x in d, and it'll still figure that out. So those are your four options. Okay. That is DECT in a nutshell. So we're good there. And now I want to talk about a new topic. It's called hash tables. And so if you look up the etymology of this word hash, the reason we use it is it's like, I don't know, corned beef and hash or something like that. Hash browns. It's It comes from like a word meaning like to chop up into little pieces. And so in essence, we're chopping up our data and coming up with a place to store it, I guess, is the idea. So we're making a small representation of what we need to put inside of like the key to a table that we're going to write. So if that made any sense, that's good. Otherwise, don't worry, I'm going to get into all of this. So this answers this question, which is an important one. So far, we've seen log n search in the best case. Okay? And what was that? That was binary search. We give it a sorted vector, sorted vec. As long as it's in order, one way or the other, we can use binary search to like have the search space. We start with all of that, maybe we need to search in the left half, then the right half of that, then the left half of that, who knows, on and on and on. And this repeated having gives us a log n runtime. Can we beat that, is the question. And without looking at the small little diagrams on the left-hand side of my screen, what do you think? Maybe pause the video, try and think of a way to do better than this, if we want to search for something. How can we beat log n? We have a bunch of elements. How do we search for them? And, well, the simplest way to do that is, the answer is yes, by the way. The simplest way to do that is, let's pretend we only ever need to insert and search for the numbers 0 through 100. Okay? So, guess where I'm going with this? Why would I want numbers arranged in this manner? What could I use those for? Okay, if these are the only things I could ever search for and insert, well, I can do very fast operations and get them out of, drumroll, a vector. Yeah? That's the idea. So we can make a vector with indices 0 through 100 and just plop things in there and take them out. Look and see if those things are there. We'll call it a lookup table. So we'll fill it. This is, if you've never seen this constructor of vectors, it's very useful. It is, well, it's a special one, vector of bools, but we'll just go to the normal vectors constructor. It is, where are you? Fill, we're using the fill constructor. So we're going to make a vector of a certain size. Oops, sorry. I wanted to go back here. I guess it needs to be 101, or I can say 99. Let's just say 99. It'll be a vector of size 100, and I want to fill it with nothing but false. So what that's going to make is this variable called lookup table. It's going to be a vector, and it's going to have 100 things, and they're all going to be false. I'll use F. F, F, F. Because nothing's in it right now. There's 100 items. So that's a really nice constructor for vectors. It's called the fill constructor. You give the size that you want, and you give what you want to put in it at each index. So it initializes this entire vector to be of size 100 and holding a bunch of falses. And so the idea is, if I want to search, or if I want to insert 42, I can say lookup table dot at 42 equals true. I'm saying it's there. That's me saying that. So that's insertion. Search is now, oh, I'm looking for 42, is lookup table dot at 42, at that index, this one in here somewhere, is it true or false? And we just made it true. Is 42 there? So this is insert, this is search, and if you remember these basic operations that we were talking about, this is essentially going down into some array somewhere and indexing into it, which is super easy to do. It's just some address calculations involved. It's constant time. So we just solved this problem for searching for numbers with a special arrangement of those numbers in constant time search. Binary search, you suck, man. You're log of n over there. No, we can do better than you for certain cases. Now, that's a lookup table. We had a very constraining thing. This is a pretty large constraint. Dot, dot, dot. Let's see how we might solve that. Okay, hello. This is going to be a horrible edit, but I want to re-explain this slide. So lookup tables, they're really, really nice when we don't care about the order in which we store the data. So for example, first maybe we insert at index 27, then we store like at index 13, then at index 42. Like the order is completely wrong here, right? There is no order at this point. So if we don't need to know like what's the next smallest value, then a lookup table is a really good idea. Okay, and some example that's close to something in real life is the idea of a reverse phone book. So you get a call from somebody that you don't know, and you want to see if it's like a telemarketer, so you look it up on Google, right? So you can make a reverse phone book kind of vector. Like so at a certain index, the index of the phone number, you can store who called you, okay? Things like that. So you can use a lookup table for that. You can say, all right, this is a vector of, I don't know, I guess you need 10 million different strings to store phone numbers, but it's a vector of 10 million strings, okay? So this idea of a lookup table is quite powerful, and we'll make it even more powerful in the next slides. It can be any kind of association between numbers and then whatever value you want. So an index into this table to a certain value, okay? And we're going to make that even better next time. We're going to make it between any kinds of values to any other kind of values, all right? So that's the idea. And because you can use vectors here, you can immediately get to places in vectors if you remember all of that stuff about computational complexity. So I am going to say that insert, if I can spell insert, is O of 1, right? You can just go to the index, look up and see if it's there, okay? Or sorry, put it in there. And then if you're tired of the key, we call these things keys. If you're tired of that being in your lookup table, you can remove it, and you can set it equal to some specific value. And again, that's just go into the table, set it to some value, constant. And then retrieve, or lookup, is again constant. You just go to the table at the index you're looking and see if it holds a value, and if so, get that value. Okay, so that is what I want to say. This is going to be another horrible edit away from this, and I will see you in the next slide. All right, and I guess I should prove it to you a bit more than that. Insertion, removal, retrieval. I'm claiming that these are all constant, and I'll prove it to you. So assume going to an index of a vector takes constant time. And that really is the case, okay? With that, I can prove that these are all constant, okay? Constant time. And running time, that is. We'll then talk about space. Okay, so it's constant running time because I just need to index into whatever index I'm looking at. And set the value there. If I'm trying to remove something, I need to get rid of the value, like set it to some special removed value. Or like non-existent. Like the equivalent of false for our original lookup table, but for like strings or something. Maybe it could be the empty string. Like it's not there, we got rid of it. And then retrieval is constant running time, because again, you're just going in to whatever index you're looking at, like index 42, and you're not setting the value there, but you're getting the value there. Okay, so like you're looking up here, hey, what's at index 42? Is it true or false? And that's again just going to a place in a vector or an array, super fast. Okay, so that's running time, time complexity. Let's talk about space complexity of lookup tables. So the space complexity of a lookup table is the largest, it's the size of the table itself. And so if I was storing phone numbers, for example, is a 10 million size table. And this is technically constant space, which is kind of hilarious, but still very bad, right? I don't have 10 million numbers to store. Maybe I just want to store my friends. Like 100, okay? But you need this much space so that you can store every individual number. All right? So that's the issue. When we want to insert a wide range of numbers, or just a small amount of them, we're kind of screwed because, all right, let's pretend we wanted to enter the student ID numbers of everyone in this class. How about that? Well, your ID numbers are very long, right? Most of them start with a 0 for some reason. That's like 8675309. Again, super long. But there'll only ever be like 50 students max. But if I want to make a lookup table that takes these kinds of numbers to values, like the string that is your name, or your grade or whatever, that's going to be an issue, because we have to make so much extra space just to store 50 ID numbers. Okay? That's a problem. And the idea is, no, we don't have to do that. There is a simpler way. Instead of making like a size 10 million vector, and only using like 5 things, what a waste. What if we could use a much smaller vector? How might we do that? And so this is what the word hashing means, okay? We want to shrink down our large input space into a small range of values, okay? So the idea is, let me pick all my friends' phone numbers or something. 1, 2, 3, 4, 5, 6, 7. Here are all these phone numbers. Then, I don't know. Now I'm just making up random numbers. 5, 5, 5, 5, 5, 5, 5, and then, I don't know. Let's see here. That'll work. So these are numbers, like just write them all out, forget the dash. We want to shrink down our large input space to a small range of values. So instead of making a size 10 million array to hold these, let's see here, we can make a much smaller one. All right, so let me show you the problem, just to drive it home. I'll make a vector, and it's going to need to hold 10 million. 1, 2, 3, 4, 5, 6, 7. Yeah, 7 zeros. 10 million elements. Okay, so that's my vector for phone numbers. And all right, let's go and implement my enter my friend's numbers. All right, so 8675309. Equals, well, let's make it strings, I guess. Lawton, I don't know. Now let's do this for everybody else. 1, 2, 3, 4, 5, 6, 7. These numbers are actually, I chose them in a special way, so this will, I do want to copy them. 1875306. At least I chose them with a special last number, and this will become apparent later. All 5s. And then 9876543. Alright, so this is Lawton. Maybe this is my mom. This is my dad. This is my sister. And it's the age of information. My cat has a phone. Okay. So this is our lookup table. It's way too big. But it works. It'll still work. I can be like, all right, whose number is in these 8? Whose number is 8675309? And it'll work. It'll run. It'll print it out for me. Hashing example. Hashing example. Yes, it's Lawton. And you saw that take some time to run because it had to allocate so much space. That's a problem. Well, what we can do, though, is if we don't want to make a giant vector, let's make a vector of size 5 or something close to 5. Because we only have 5 things. So let's pretend we have n things. We can make a vector that is on the order of size n. Okay, so we might need some extra room, and I'll explain that in a much later lecture, but let's store it so that we don't have to store a giant vector with 10 million elements, but something closer to 5. Okay? In this case, we can actually get away with 5 for a reason that I'm about to explain. We want to shrink down this space, all these different numbers, into a small range of values that can hit every part of our lookup table. Okay? To a unique place, ideally, and we want each index of the lookup table to be equally likely to choose. So how can I shrink these 5 numbers into, oops, how about 6? 6 will be easier. Or no, 10. How about 10? That'll work. All I need is 10 elements. And here's the key. Here's one way to do it. I can shrink this number into 9. I can shrink this number into 7. I'm just taking the last one. I can shrink this number into 6. I can shrink this number into 5. I can shrink this number into 3. And what do you know? I can insert all these things. I'm going to make a special function to do it just so that I explain the process. But I can go and insert all of these things now with a call to this new different kind of function. Oops. I always get these confused. And then this will be deleted, replaced with a comma. And then oops. Okay. That's what I want to do. I want to make this function that inserts it, though. So I can hash these keys. That's the name, that's the word. I can hash these phone numbers. Because I never need to retrieve them, I'm using them to look up. Okay? Insert into vector. Oh, I guess I need to put the vector itself. Boop. Be with hashing. There we go. So I'm going to take the vector. I'll take it by reference so that I can set it. Int n. Yeah, this will be called the key, and the string will be the value. So this is the terminology. I'm inserting into my lookup table keys that are mapped to values. So those are the two keywords here. In my example, phone numbers in this example are keys, and names are values. So stored in each index of my special lookup table, I'm storing strings. Okay, so this will just be void. And so here's what I'm going to do. I'm going to hash. That's the word. Hash the key so that it fits the valid index into V. Okay, so key hashed equals v.size, that's only 10, and it's going to be key mod that. It'll always be separate, because always end with a different number. Mod 9, or taking this number, modding it by 10, taking the remainder by 10 will give me the 9. This one will give me the 7, the 6, the 5, the 3. Okay? So they'll all be sent to a different place for my particular example. That's nice. And then I can go and insert v dot at the new key, the new hashed version, equals the value. All right? So now I can totally do the same thing, but I need to hash again. Okay? This is not the same. So let's separate this out. Let's say hash. So this function hashes and a value x. And so my hash is going to be mod 10. Okay? So let's do that. Alright, that'll be my hash. And I think this has already been overloaded, darn. So I'll call this phone number hash. How about that? That works. And so then I can look up v with hashing, the same place, look up the same value, but I just need to hash it first. Okay? Hopefully this terminology isn't too bad. I'll be using it so much more that it will get used, that you'll get used to it. So it's not a big deal. Okay. So watch this. Print Lawton. Wow, and it worked, and it's so much faster. I only needed to store 10 separate things. A lot less wasted space. Okay? Let's see here. So what I want to say is we shrunk the input space. Through hashing, we shrunk the input space, and so now my vector only needs 10 indices. It had 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And what I did, the secret was, I noticed that I could separate all of those values that I would ever want to search for based on some mathematical operation, which is mod 10 in this case. So this fancy number, if I ever want to look it up, I'll just instead look at 9. I'll hash it. I'll hash it first and store Lawton there. Lawton. And then at 7, I'll store mom. And then at 6, I'll store dad. Because if I ever look it up, I just need to remember to go to not the numbers index, but the hashed numbers index. Okay, so if I hash it, I get the 6. And then I'll find dad's number, or I'll find dad's name based on the number. Okay, at 5, I have my sister. And then at 3, we have my cat. All right, that's the idea. So hashing allows us to shrink the input space drastically. Okay, so even if you're trying to store a lookup table that takes large numbers to values like strings or whatever, you only need to store on the order of that many elements in your vector. Okay, size of n. Okay, so that's a basic idea of hashing. I've given you an idea of how it's going to work. You just shrink your vector and just make sure to look up using the hash, which is some special mathematical function, and that'll get you to the right place in this vector. Okay, it'll take you to the right spot where you stored that thing originally. Okay, then you can get the value back. So that is a lookup table. It is linear space, constant time to look up, lookup time. That is killer, and that's beautiful. And there are some more problems that are going to arise when we talk about this, and there's some more things that we would want to do. Why can't we just take names to numbers instead? Why can't we do the opposite? Well, we'll find out. We'll find out how to solve that problem, actually. It's not an issue. We're just going to have to somehow turn names into numbers so that we can do the reverse, take names to numbers in our dictionary, in our phone book. Okay? No more reversals. So with that, that's where I'm going to leave you in suspense, and next time we're going to talk about hash tables in depth. This was just a taste. And so let's get into some exercises, really just one, as many times as you want to do this. It's a really good one, I think, and that's where I'll leave you. So what I would like you to try, if you're feeling game, if you're up to it, try combining all of these data structures that we now know about, because at the end of the day, after this class is over, this is what I want you to remember: how to correctly combine data structures to do cool things. Think of the operations you need to use, and like make a class that follows through with everything with the best possible running time complexity and space complexity trade-offs. Okay, that is the goal of this class. And so one way to get there is to start thinking about what complicated data structures made up of data structures look like. Okay, complicated ADTs made up of ADTs. So I would like you to try to make a list that holds inside of it stacks, that holds inside of that each stack holds a queue, and each queue holds elements as ints. Okay, try that. And then I want you to pick a random element inside of one of the queues, pick a random int, and see how you might get there. What operations do you need to perform to get there? That is going to be super helpful. So on the outside, we have a list. It's going to be a very long list. I'm asking you to insert 3 things. 3 giant things into this list. So inside of each list, I want you to insert a stack. So here's our stack. And that should hold 3 things. Yeah, let me start using different colors. Let me alternate. Boop. 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 I better start writing tiny. Let's fill up the space though. I'm trying to put 3 things inside of each list element. So inside of each list element there is a stack holding 3 things. Okay. And inside of that is a queue holding 3 ints, at least if you follow my instructions. Let me go back to blue. I don't know, 1, 2, 3, 4, 5, 6, 7, 8, 9, 3, 2, 1, 6, 5, 4. How would you make this happen? What code would you need to write? This is super helpful. I think you should really give it a try. 2, 1, 3, 5, 4, 6, 8, 7, 9, whatever. And then pick, all right, I have this complicated data structure. I want this 5. How in the world am I going to get to it? What do you need to do? Well, you need to get to this place in the list. You need to find this node in the list. Get there. All right, once you're there, look inside of it at the stack. And it's not the top thing, so you better pop. Pop so that you can start looking, getting closer to your answer. You better pop that. And then inside of that, top of the stack, now this is the new top, you have a queue. And oh man, this is the middle element. It's not the front yet, so I better pop the queue. And then suddenly I have my 5. Okay, so play around with this. Make up your own combination of things. Maybe include vector somewhere. But you can combine them in these things in this way, and it will be very, very helpful to learn just exactly how to maneuver around this kind of complicated mess of a bunch of data structures and slash ADTs. So with that exciting plan, I want you to get started there, and good luck with it if you try. And that is all I want to leave you with. I'm going to record a lab video, and that is where you will see me, and then you are done with me for the week. So I'll see you then.